master's review of Kurt Borum. That Kurt comes to us from Bradley University, where he innovated mechatronic devices. Here at Carnegie Mellon has contributed broadly to planetary rover research and field experiments. For his master's concentration, he has investigated the techniques and merits of utilizing absolute bearing from the sun in order to improve navigation. The committee is George Cantor, Heather Jones, myself, and here's Kurt.
Thank you, Red. Thanks everybody for being here. As I mentioned, the title of this thesis is Improving the Localization of Planetary Rovers with Absolute Bearing by Continuously Tracking the Sun. Keyword being continuously. So here on Earth, we have things pretty easy for our outdoor robots. If we need them to find an absolute heading, there's a magnetic field. They can use a magnetic compass. We've got GPS that covers almost every inch of the planet that we can use to get a absolute position fix. So why would we be interested in looking at the sun and using it to give us this information? Well, a big reason is that none of the planets or moons we're interested in exploring with rovers have magnetic fields that are suitable for magnetic compasses, and none of them have the GPS system or the infrastructure in place for absolute position or absolute heading measurement. So one thing you're always guaranteed if you have a view of the sun is one of the best absolute heading reference objects in the solar system. Brighter than anything else, and its movements can be predicted extremely precisely using what's called an ephemeris, which is typically a computational table or model. We use one from the JPL laboratories, and if you give it a time of the year, it will tell you the relative positions of all of the celestial bodies that are included in the calculations. So it makes it relatively trivial to find what angle the sun should be at. So this thesis asserts that using the bearing from the sun will substantially increase the accuracy of route determination compared to using a relative heading estimate from IMUs or from visual odometry. And in our experiments, we were able to outperform an inertial measurement unit or heading tracking gyroscope with the solar compass and real odometry working together without any other measurements. And or it performs about as well as some examples of visual odometry I will show later, where they've used the visual odometry with the solar compass. We were able to get similar results using a solar compass and just wheel odometry. So when you want to do path reconstruction without absolute bearing, things get a little tricky. It's very simple to do. This is a very simple model of kind of a minimalist formulation for reconstructing the path that a rover has driven if all you know is that you've been counting the turns of the wheels, which is one of the measurements we've used in our experiments. In this case, it averages the amount of travel of the wheels on each side and uses that to determine a change in distance. And it also uses the change in wheel turns on left and right and the width of the rover, the wheelbase of the rover, to determine how much the rover has turned given the turns of the wheels. If you notice, there are several error terms in here, particularly in the heading calculation. And these errors continuously add up incrementally, and your solution will quickly diverge even after a relatively short amount of time. So even if you have a really good sensor, you're not immune to having your wheels slip on the ground, which in the type of robot that we're using here, this is commonly called a skid steer or differential drive robot, where wheels on the right side and the left side move independently. So to turn left, you turn the left side slower than the right side, and vice versa. It's very simple and very popular configuration, but it's very susceptible to wheel slip errors during turns because the wheels physically have to slip. It's not like a car stand where your wheels can comply with the ground. And on rocky and challenging terrain, such as the surface of moons and other planets that we're really interested in, you're guaranteed almost that when you do point turns, you're going to be slipping over rocks, and your errors are going to be unpredictable. So this is an example of what a route reconstruction using this might look like. Even if you have very good wheel odometry measurements, it only takes one bad measurement to ruin your path reconstruction from that point on. And without some sort of absolute reference, it becomes useless for navigation very quickly. So if you can have a way of getting absolute bearing, these blunders and drifts from incremental errors can be bounded or limited to a certain range or growth rate. If using absolute bearing, you can drastically improve this route determination and make it usable when beforehand it wasn't. And like I had mentioned earlier, the sun is one of the best sources of absolute bearing that you could ask for. And it works well with rovers because a lot of times they're solar powered and are required to be in direct view of the sun. So solar compass is it's a relatively precise instrument. Gives you the absolute bearing to work on any planetary body with a view of the sun. There's no special infrastructure needed. All you need is a way to observe the sun and an ephemeris, and the calculations are relatively simple. So the technique of using the sun as a compass is as old as civilization almost. And it's still used on spaceships, spacecraft, modern rockets as an absolute orientation method. It's usually the first method used before going to a really high precision attitude control using star tracking devices, because the sun is so easy to find. Okay, so this is prior work done in 2011, 2012 in Canada using a space-grade solar compass or sun sensor, which has a limited field of view, only about 90 degrees that it can see compared to ours, which we'll talk about later. But this shows they pushed this rover analog through rough terrain for about 10 kilometers. And over on this side, there's a column. This is using just visual odometry, and this is the percent error. After, for instance, here they went 124 meters and had a 3.3% position error at the end of that trek. When they used the sun compass, it halved that for this small. Some of the larger ones had more dramatic differences, cutting it down by half by adding in the sun sensor. And we'll show later how our numbers compare. So the theory of operation of the sun compass is a lot to take in right here, but I'm going to go through it step by step. So if you can see up at the top, we have a 187-degree lens. We use a camera, and it's a commercial off-the-shelf security camera. So it has a very wide-angle field of view, wider than commercial sun tracking sensors. And one thing that this research did differently than what has been done in the literature was not to use solar filters. So the amount of solar radiation coming into the camera was not reduced. And so you can see up here, without a filter, there's a lot of glare. It's very bright. But this research underexposed the image severely, which had a couple of effects. One is it reduces the glare and gives us only a small area of very bright light. And the other thing it does is give very crisp images, so it allows us to take images very quickly without getting motion blur. So going over rough terrain, That was one problem with this experiment that they experienced, was they would have to stop and wait before they could get a good reading with their sun compass. With the sun compass developed herein, there was no need to stop and wait. And about 12 centimeters a second is what the rover was capable of. It never showed any signs of blurring. So the next step in the process after capturing the image is to detect the sun in the image. And this took a couple of iterations to find a robust method. So this method first does a Gaussian blur that smooths out noise in the image, and then segments the image into a binary image where every pixel is either labeled a 1 or 0. And the method used, instead of just a simple thresholding, was Otsu thresholding, which is a little bit fancier, but it helps reduce noise, and it changes the threshold to fit the data locally. The next step is to find contours in this binary image where there's clusters of white pixels that are all contiguous with each other. And once all the contours are identified, this looks at the largest contour, and if the area of the contour is greater than a certain threshold, then it will check the average intensity of the pixels that are covered by that contour. So it goes back to the original image and looks at all the pixels that are contained within the boundaries of that contour and finds the average intensity of those pixels. And that allows us to find even very small sections of the sun when it's occluded or behind something, because even though not a lot of binary pixels are showing up, when it goes back to the original image, it's a very bright spot compared to other clusters of pixels throughout the images. So it worked exceedingly well when others failed. I'll show in our field test later, but there was noise, there were some lights that were not able to be turned off. And simple methods would detect them whenever the sun disappeared. This allows it, so when the sun is fully occluded, it won't key on anything, because there has to be a very bright light source that can be better parameterized and characterized this way. The next step is to compensate in real time for the tilt of the rover. This research is aimed at rough terrain where the rover could be pitched as much as 20 to 30 degrees, and sometimes in either roll or pitch. In this case, this uses a Epson V340 miniature inertial measurement unit, 6-axis gyroscope and accelerometer. The sun compass only uses the accelerometer, but it does use fused data. So we'll talk about that a little bit more later. But the lines here turned out pretty small. So this right here represents a unit sphere. And the image is taken with a spherical lens that we calibrated using a fisheye model that gives us the transformation to go from two-dimensional pixels in that image to a unit sphere outside of that image. That allows us to take the XY coordinates of the image of the sun and transform them into an azimuth and elevation on the unit sphere, and then apply the rotations, or undo the rotations that we detect using the gravity vector from the accelerometer, and essentially straighten out our view of where the sun is located. Because as you tilt, if you can imagine, as you tilt sideways, the sun will trace an arc through the sky, and it will move in the image, and we'll no longer be able to get an accurate bearing from it unless we compensate for that tilt. So this gives us an observed azimuth of the sun relative to the ground plane. The next step is to use an ephemeris to give it the date and a latitude and longitude that doesn't have to be exact, but near where we are located at. So with time and location, it will provide an accurate reference azimuth or relative bearing. And the difference between the observed azimuth and the reference azimuth is the absolute heading for the rover. And as you can see at the top, this is a simulated image of the top-facing fisheye camera. You can see the horizon wrapped around the edges and up the top of the sun. And as the rover turns, this image rotates about its center, and the difference between these two vectors is our absolute heading. This is the process that was used to calibrate the sensor, using typical computer vision calibration targets to get the parameters to model the lens, and to test the precision of the device and make sure that the IMU is working correctly. This is a custom-made 3-axis gimbal using machining equipment and camera pan tilt equipment to precisely move this. So this has the camera, and underneath the plate the camera is attached to is the IMU as well. So this sun sensor was used on the Andy rover for a lunar polar analog field experiment that was done at night, which is a unique test that we haven't seen in the literature. It allowed precise control of the lighting conditions, which is one of the problems facing a solar compass on Earth, is the atmospheric effects, particularly cloud cover, particularly in Pittsburgh where it's cloudy a lot. And this allows a performance similar to what we would see on the south pole of the moon, particularly. This test was performed here in a large trench that's roughly 10 to 15 meters deep and roughly 300 meters end to end. This is where the light tower was. This is an example of an industrial light tower similar to the one that we used that raises the light source so about 10, 15 meters above the ground. And the light we used, this was directional. This blue trace right here is the surveyed ground truth position path that the rover followed. It started at this red arrow, drove away from the light source, then came back towards the light source and did some more maneuvering on high-angled slopes. And here is the Andy rover, the 4-wheel skid steer with the sun compass mounted to the